SUERF, the European Money and Finance Forum, bringing together policymakers, finance, and academia.
Welcome to this SUERF-ECB-Bank of Finland, Bank of Italy workshop on the use of AI in economic modeling and forecasting. Machine learning, neural networks, and large language models are swiftly being adopted in economic research. Apparently, the use of generative AI is actively explored and embraced by economists in academia, central banks, think tanks, and the financial sector. This workshop brings together cutting-edge research in two specific areas. First, the solving and estimation of economic models, and second, business cycle and inflation forecasting. This workshop is the third event SUERF is organizing on AI-related topics this year. The previous ones were on 22nd April on AI in central banking and on 20th June on AI in banking and finance. It's also part of a longer series of SUERF events in economic modeling and forecasting, the latest one of which was on 4th June on ECB macroeconomic models for forecasting and policy analysis. Before we start, let me thank the members of the scientific committee, Mathieu Darac-Parier, Hanno Kase from the ECB, Juha Kilponen and Esa Jokibolle, Fabio Verona from the Bank of Finland, and Alessandro Notarpietro from the Banca d'Italia for the great cooperation. Without further ado, let me hand over to Mikael Juselius, Bank of Finland, who will moderate the first session.
Thank you, Ernest. So the first session is on solving and estimating macroeconomic models and using deep learning. We'll start with Hanno Kase from the ECB on estimating nonlinear heterogeneous agents model with neural networks. Hanno, go ahead.
Thank you. Very happy to present my paper together with Leonardo Melosi and Matthias Rottner, titled Estimating Nonlinear Heterogeneous Agent Models with Neural Networks. The motivation for this paper is that those heterogeneous agent models, or HANC models, have gained more and more popularity because they allow us to study those very interesting questions that about social inequality, about how idiosyncratic risks matters for the aggregate dynamics, and vice versa, how aggregate risks matter for the individual decision making, and how those policies, aggregate policies, shape income and wealth distribution. And these models, although they are very interesting, they're also very complex, and because they are very complex, they're also quite difficult to solve, especially the versions where you combine the heterogeneous agents, so who face idiosyncratic risk, with some, aggregate uncertainty and aggregate nonlinearities. And they're especially difficult to estimate because the standard procedure for estimation require us to repeatedly keep solving those types of models. So what we propose in this paper is a neural network-based framework for estimating exactly those types of nonlinear heterogeneous agent models. And we achieve this by introducing two key innovations. The first one we call extended neural network, and this allows us to avoid this repeated solving of the model. And the second one we call neural network particle filter, and it will reduce dramatically the cost of likelihood evaluations. So let me tell you a little bit about the first innovation, and starting a little bit further away. First, how would we even use deep neural networks to solve these types of models? And whichever paper you look at, the broad outline or the steps are more or less the same. So since we have heterogeneous agents in the model, we have distribution as one of the objects for the state. And since it's infinite dimensional object, we have to deal with it some way, and how we deal with it is we replace it with some sort of empirical distribution of L agents. So this is the step 0 that you would do if you have heterogeneous agent model. The second step would be to parameterize some individual and aggregate policy functions with deep neural networks. Second step would be to construct a loss function, which is usually some sort of weighted mean of squared residuals of equilibrium conditions, such as Euler equation error, market clearing conditions, new Gaussian-Phillips curve error, and so on, depending on the model. And then you would train those deep neural networks using stochastic optimization. So you would try to minimize this loss that you constructed in the second point by drawing points from the state space, and then basically adjusting the weights of the neural network so that it starts approximating better and better the true policy functions. And then you would basically simulate the model forward to generate new draws from the state space and repeat the optimization process. So this is how you would solve the models. But for estimation, this procedure is too time-consuming, too cumbersome. So what we introduced is this extended neural network, leveraging exactly the fact that the neural networks are very good at approximating high-dimensional functions. So adding state variables is relatively cheap. So we basically modify the step one. So now the neural networks that we have, they don't only take as inputs as the current state of the economy or the model. They also take as an input a particular kind of parameter combination that we're interested in the end estimating. And we also modify a little bit how we train those deep neural networks. So now when we simulate the model to generate new draws from the state space, from time to time, we will also draw new parameters. So in the end, we will have this neural network that gives us the correct or the true policy functions, the optimal policy functions, not only for different state values, but also for different parameter values. So although this is much more complex problem than just solving the model, we only have to do it once. So we will avoid this repeated solving of the model. And just to illustrate what we get out of this extended neural network, I have plotted here a surface, two surfaces for a very simple model. On the left, we have a policy function for inflation, and on the right, we have policy function for output, and they're conditioned on the state and also one of the parameters. And normally, if you would solve the model, you would get only the dashed black line. So you would solve the model for a particular parameter combination, but with our extended neural network framework, you would basically solve it for entire parameter ranges. So here I have, of course, plotted only for one parameter, but this neural network, it's a high-dimensional object, so it can have and will have multiple parameters. And if I want to estimate, I don't have to repeatedly basically solve the model. I will just pick a parameter combination I want to have the solution for, and then this neural network will produce this optimal policy function, or for example, how much a household would consume with a particular state value, particular assets and income states, and particular parameter combination of the model. So now we have, with this extended neural network, avoided this repeated solving of the model. But if we're working with the nonlinear models, calculating the likelihood, we have to use some sort of Monte Carlo filter, or at least that's one way of calculating the likelihood. And although we're not solving the model anymore, we still need to evaluate those neural networks that give us the policy function for thousands of parameters and hundreds of time periods. So although this neural network evaluation is really quick, once we start doing it hundreds of thousands of times, it becomes a bottleneck. So what we introduce is this neural network particle filter. And this is a very sort of simple supervised learning solution to this problem that we introduced. Namely, we used a regular particle filter to create a data set of parameter values and log likelihoods. Then we split this data set into training and validation samples, and then we train a neural network on the training sample and use the validation sample to check if we're overfitting or not. So in the end, we will have this neural network that maps directly from parameters to log likelihoods, and that essentially gives us almost instantly the likelihood of the model for parameter combination. And one interesting benefit of this approach is also that it smooths out some of the noise in the particle filter, as illustrated by this plot. So here the orange dots are the sort of raw output from the particle filter. The blue line is the fitted neural network, and on the horizontal axis I have different parameter values. And in the paper we have several examples of using this approach. The first one that I will cover also in this presentation is solving very simple linearized 3-equation neural network, New Keynesian model that has analytical solutions, so we can compare what we get with this extended neural network approach to the true solution of the model. We have also a comparison with a very simple nonlinear representative agent New Keynesian model with aggregate nonlinearity. And the point of that exercise is to show that standard estimation procedure and our neural network-based estimation procedure produce very similar results for nonlinear models. And finally, we also have a nonlinear Hank model to show that we can scale this up to larger, more complicated models. And that there we do 2 exercises, one with simulated data and one with aggregate time series from US that I will talk here. We'll now talk about linearized
5 minutes, Hanno.
New Keynesian model. So so it's very simple. It has 3 equations and it has analytic solution. So we follow these steps. We have one neural network that has one state and then takes 8 parameters as inputs and produces this output gap and inflation as predictions. We construct the loss function, and if I go back one slide and you check the loss components and the model equations, then it's immediate where they come from. And then to train this deep neural network, we use stochastic optimization, and each step of this stochastic optimization, we have a batch size of 1000, which you can think about as sort of parallel worlds where there are different state realizations, but also different parameters potentially. And we train it over 500,000 iterations. And in each iteration, we draw parameters from this bounded parameter space. We simulate the model forward, we compute the loss, and then we take the optimization step, and we use the standard sort of Adam optimizer to adjust the weights of the neural network. And here I have a comparison with the analytical solution. So analytical solution is the red dashed line, and the blue line is the neural network solution. And you can see that it lines up perfectly. So it's very accurate. Now, we have also a third example in our paper is the nonlinear heterogeneous agent models. So it's a much more complex model where we have idiosyncratic household-facing idiosyncratic risk, but there's also sort of individual nonlinearity, namely there's a borrowing constraint. We have 3 aggregate shocks: preferences, growth rate, monetary policy shock. We have aggregate nonlinearity in the form of zero lower bound. And here, basically, we follow the same steps. And the very first step is to somehow approximate the distribution of agents. And for this application, we use 100 agents. We have more deep neural networks to approximate policy functions. We have one that is sort of like an aggregate policy function that gives us the inflation and wage. and then the individual one that gives us the labor choice of the household, and we can back out everything else from that. The loss function is composed of several components, something that's called Fisher-Burmeister equation, Newgation-Phillips curve, and then market clearing conditions. And then we train the neural network. But let me skip this part for interest of time. So once we have those extended neural networks, we do the second step, namely this neural network particle filter. And then using this neural network particle filter that gives us the likelihood, we can run the random walk Metropolis-Hastings algorithm very, very fast, because most of the computational cost is front-loaded. And for the estimation sort of exercise, we use time series data, only use 3 time series on output growth, inflation, and interest rate. And these are the parameters that we get from this estimation. So what's interesting about this approach is that there's essentially no difference if we want to estimate parameters that affect the deterministic steady state or some sort of shock parameters that are like equally cheap or expensive. And let me finish with some plots about the results that we get from it. Is what's interesting in this model is that when we increase the amount of idiosyncratic risk in this that the household face, so the red dashed line here is basically the parameter for the idiosyncratic risk that we get from the estimation, and the blue line is when there's less, and the dashed black line is when there's more idiosyncratic risk. We see that from the right chart that the interest rate is more frequently constrained by the zero lower bound. And on the left chart, we see that this zero lower bound also introduces sort of kinks in the policy functions, and those kinks kind of are kind of in different places depending on how much idiosyncratic risk is there in the model. And if we have more idiosyncratic risk, so here the idiosyncratic risk is on the horizontal axis, we will also increase the frequency of the CLB episodes. So here we have blue line is a model with CLB, and then the red dashed line is a model without CLB, but kind of calculating the times or the frequency at which the interest rate is below the zero. So we see from here that if we increase the idiosyncratic risk, then more times we're at the CLB, which also means that in the end, the standard deviation of the output will be much, much higher when we have more idiosyncratic risk. So to summarize, what we have proposed in this paper is a novel estimation procedure, and we base it on neural networks exploiting their strengths. And we introduced those 2 key innovations. First one we call extended neural networks, and that allowed us to avoid this repeated solving of the model. And the second one is the neural network particle filter that allows us to do really quick likelihood evaluations. Recently, we released a code for the analytic example, so you can find the code either from a link from my website or this QR code. Thank you.
Thank you, Hanno. We have about 6 minutes for Q&A, and given the number of participants, I guess it's easier if Hanno looks at the chat first.
So there's first question was about which kind of artificial neural networks are we using? We're using, yes, the feed-forward neural networks. In principle, the second question is about basically on which kind of Hank models is this neural network estimation applicable to. You could, in principle, apply it also to tractable Hank models, but the kind of idea of some of those tractable Hank models is that they have either very quick or analytic solutions, so you don't necessarily need this computational framework, because you're avoiding the costly computations by just designing your model such that it has those analytic properties. But in principle, yes, basically our approach doesn't really matter if it's representative agent, if it's heterogeneous agent. And in fact, we saw one example where we did analytic model, although we don't really have to. It was just for demonstration and to check the accuracy. So third question is about mathematical properties. So what we are not imposing some convexity or monotonicity properties, but we are imposing like let's say sign sometimes, or a range if we know that, for example, the reasonable range for parameters like or the outputs of the neural network, like inflation is, I don't know, if we have some sort of prior about it, we can impose it with a very simple sort of activation functions in the end of the neural network. Fourth, there's a question about overfitting. The overfitting really isn't a problem for this extended neural network approach, because we're constantly kind of generating new data, and we're not doing like a supervised learning. It's self-supervised kind of type learning, where essentially there's no issue that we will kind of fit too well to a particular data set, because every draw that the neural network sees is kind of unique and only used once. Regarding the neural network particle filter, we typically don't have too many problems with overfitting, but just to be sure, we use this training and validation split, and then we can just check that the validation error doesn't start increasing basically in the end as we train. So there's a question about why would it be better to estimate rank models with neural networks than with Bayesian. So to clarify, this is likelihood-based Bayesian estimation routine that we're proposing. Why would you do it with our approach? Perhaps some of it is that you can kind of front load some of the computational costs. So for example, this rank model, although it's a very simple model and we can do it with standard procedures, our neural network-based estimation procedure is in terms of timing results, it's competitive, and for more complex models, you might not be able to do it without actually neural networks. So there's a question about the size of the neural networks. More or less everywhere we use 4 or 5 layers, and each layer is like 128 nodes wide. So it's hard to say if it's smaller or large, because these days, there are networks with billions of parameters. But so there's a question why we're using the random walk Metropolis-Hastings algorithm. So we could, in principle, also use this Hamiltonian Monte Carlo that is suggested, because in principle we have this neural network that maps the parameters to the likelihood, and this is like easily differentiable. So we could do Hamiltonian Monte Carlo, but we also don't really need to do it, because the likelihood evaluation is so cheap that we can already do the random walk Metropolis-Hastings very quickly. So at least, okay, there are other properties perhaps that Hamiltonian Monte Carlo has that the random walk Metropolis-Hastings doesn't, but at least in terms of like the efficiency of proposals relative to what gets accepted, this is not, we don't have to worry about it because likelihoods are cheap in our framework.
I think we have to continue.
Yes,
That was
okay.
actually all the allotted time for questions. So thank you very much, Hanno. That was a great presentation. We continue with Marlon Azinovic, who is presenting his paper, Solving Life Cycle Models with Rich Asset Structure Using Deep Learning. Go ahead, Marlon.
So thank you so much for having me. I'm very excited to be here and to be talking about solving lifecycle models with a rich asset structure using deep learning. So this talk will be kind of an overview talk, and so based on two papers of mine. The first one is meanwhile old. The first working paper was in the spring 2019. Meanwhile, it's published and it's called Deep Equilibrium Nets. This joint work with Luca Gegoffs and Simon Scheidegger. And the second paper I will talk about is my job on a paper, which is joint work with Jan Jemlichka, where we try to take more steps forward, addressing remaining challenges we had in this context with portfolio choice and deep learning-based solution methods. So let me dive right in. So the problem we are trying to solve is that if we want to use economic models that have aggregate risk as an important part of the question we want to study, for example, asset pricing, then we often require global solution methods. And to compute equilibria in these settings, what does it mean? It means that we have to find functions that map the state of the economy to the endogenous variables of the model. This is very similar to what Hanno just said, just Hanno additionally included parameter values. But taking one step back, purely computing for fixed parameters, the equilibrium means that we need to find functions that map from the state of the economy to basically all quantities of interest, which include consumption, savings, and maybe which asset do households buy. And these functions jointly have to be consistent with the model. What does it mean? This means that they have to be consistent, for example, with optimality conditions for households, with optimality conditions for firms, and with mark clearing conditions. And finding those functions which solve those model equations, these functional model equations, turns out to be a computationally demanding task, especially when the state of the economy X, which I denote here as capital X, as boldface X, is high dimensional, and if the function you want to solve for, which I denote as fi of X, are nonlinear. We want them to be flexible. And both of these things happen naturally in overlapping generation models. Why? Because in an overlapping generation model, we want to keep track of different age groups, which means that the state of the economy includes at least a wealth distribution across age groups. And if you have more than one asset, this distribution is not one-dimensional, but at least maybe two-dimensional if there are two assets. And additionally, we may also want to keep track that different age groups are exposed differently to aggregate shocks, and that at different ages they hold different portfolios, which then also increases the state space. And to address this challenge, there is a recent literature emerging which uses deep learning to compute those equilibria. And in particular, I will be talking about two papers. So the first one was a joint paper with Luca Gegoffs and Simon Scheidegger, where we introduced the basic idea how to use deep learning to solve for equilibria. And then the second paper is more recent. My job on paper is that we take two steps forward specifically to address challenges in the context of portfolio choice. And I focus on these two papers in my talk because this is the ones that I know the best, because these are the ones that I have worked on. But I also want to say that there are other related and very interesting papers that I can very much recommend. Looking at the literature is very new, but it's also moving quickly, which makes this very exciting. So let me start with the basic deep equilibrium nets. That's what we recorded, and let's start with the basic idea. So what we want is we want to compute functions f, which are consistent with the equilibrium conditions. So think optimality conditions, market clearing, Bellman equations. And these conditions can be written as a set of functional equations. And we want to find those functions f that for all states x, these conditions are true. And the basic idea is now that we use a neural network, which I denote as n rho. So rho are the trainable parameters of the neural network. We want to use the neural network to approximate this function. But how can we ensure that our neural network is close to the function we want to approximate? So in the standard deep learning way, what we would need is these input-output pairs, which is often called labeled data. We would need x values for which we know the true output, and then we would train the neural network to do a good job in those outputs. For example, by taking a mean squared loss over those points we have. And then we hope that a neural network generalizes well, and if it's does well at predicting these points, then it also does well on other points. Of course, there are some more details, but I'm trying to give an overlook here. But this we cannot do. Why can we not do this? Because we don't know the true outputs. So because it's the very thing we want to solve for. And this was the kind of one of the main realizations of our first paper, we do not need the true outputs to train the neural network. Why? Because all we need is a loss function that tells us how good or bad our neural network is at approximating the solution. And then we can train it to get better at approximating the solution. And what can we do? What would I use to check whether the function is good or bad? Is exactly those equilibrium conditions. Because without knowing the truth, we can still plug in a function we have, a neural network we have, into those conditions and see whether they are zero or not. Because these conditions are exactly what characterize the truth, the functions we seek. So we can plug it in and then use the error directly in those conditions to train the neural network to get better at fulfilling those equilibrium conditions. And this is great because now we do not need this label data, which means that data availability overfitting are not a concern, because we know that for every x I plug in, these have to evaluate to 0. And if they are not evaluating to 0, I want to improve my parameters to get better, to get closer to 0. In practice, of course, we cannot try all x, and especially if x is high dimensional, if the state is high dimensional, we cannot sample all of those states. So what do? What are the x we care about? It's exactly those where the model lives, those states that the model would visit in equilibrium. And what we do to address this is we iterate between simulating states from the current policy we have, from the current neural network we have. Then we try to improve the neural network on those states by reducing the error in the equilibrium conditions, and then we iterate on that. So to be more concrete, we simulate a set of states by simply drawing random shocks and simulating the economy forward. Then we evaluate the condition on this data set. In the beginning of training, the errors will be very large, but then we adjust the parameters to get better, to reduce the error. Now we have new policy functions, a new neural network, new equilibrium functions. So we simulate a new set of data. And then we again look at the error and we adjust the neural network parameters to get closer to fulfilling the equilibrium conditions. And we do this iteratively until we are happy with the error we reach. So let me illustrate a simple overlapping generation model to be concrete on these methodological points. So let's consider a representative firm that produces with capital and labor, and there's one shock, which is the productivity ZT. And this shock evolves according to AR1 process, and we also assume that it affects the depreciation of capital, which makes capital more risky. Households can trade in two assets, one risk-free one-period bond in fixed supply, which is traded at equilibrium price PT, and in risky capital, and we assume borrowing constraints, so households cannot borrow. We assume it's an overlapping generation model with one representation per cohort. Households live for 32 periods and then die deterministically. At each age, they get a predetermined efficiency units of labor, which is the typical life cycle shape, and supplies this labor exogenously, and they can choose to save in both assets, capital and bond. Capital is subject to adjustment costs. So what is the budget constraint? The consumption of households at given age is given by the labor income plus what they get from the bonds they purchased the last period, plus what they get from the capital they purchased the last period, minus what they spent on new bonds, minus what they spent on new capital, minus the adjustment costs they pay, and they do their choices in order to maximize the remaining lifetime utility. So in this model, what are the equilibrium conditions? We need market clearing in capital. This we can enforce trivially because aggregate capital is simply given by the capital households hold, and we need market clearing in the bond market. This is less trivial because we need to ensure that the bond policies are exactly consistent with the aggregate supply of bonds. Then firm's optimality can again be enforced trivially by just reading of the wage and the return to capital from the firm's first order conditions. And then we need household optimality, which will give us an equation that has to hold for each age group and each asset. So it will give us 62 equations that respectively have to hold. So how do we solve this model with a deep neural network? So the state of the economy would include the shock, the distribution of capital over age groups, and the distribution of bonds over age groups. So this is in total in a 65-dimensional vector. And what we want to find are the policy functions, meaning how much capital do households save, how much bonds do they save for each age group, and what is the bond price. And now we use the neural network to approximate this function. So the neural network will give us an approximation for this 65 numbers. And the loss function, the loss we try to minimize, is the loss in the equilibrium conditions, which is exactly the optimality condition on capital for each age group, on bond for each age group, and market clearing. So this is what we did in our first paper, and we showed at that time that this kind of works well. However, there's something that we wanted to improve, which is that now this is a little bit awkward to have all these different terms in the loss function, because implicitly the neural network now has to trade off errors in market clearing with errors with households making errors in the first order conditions for the two assets. And that makes it harder to interpret what does it mean to be solved? What does it mean to have solved the model? Which error is sufficient? Furthermore, when we simulate the model from those policies which don't clear markets exactly, also the state we generate will not be exactly consistent with market clearing, and then that can hamper the training. So in the second paper, together with Jan Jamnichka, the first thing we do is we say, okay, but why do we force the neural network to learn something that we already know? Namely that namely that the bond policy has to clear markets. And the way we do it is to basically encode that economic knowledge we have into the neural network architecture. So the way we do is we first make an initial prediction, and then we transform this prediction with a second step such that the transformed prediction is always consistent with market clearing, and we take this together. We call the last step a market clearing layer, and we take this together as our combined neural network, and all predictions of the combined neural network will always be consistent with market clearing, and hence the only remaining errors we have are the optimality conditions for households in the two assets, and we do not need to take care of market clearing anymore, which has several advantages. The second thing we realized is that single asset models are typically easy to solve, and many asset models are hard. Why is this? This is because portfolio choice is only pinned down once we have a precise solution. It is comparatively easy to figure out how much to consume and how much to save, but how much exactly to save into a bond versus a stock is a much harder problem. But if you cannot distinguish these two things, it's very hard to get to low errors in the first place. So what do? We realize that every n asset model essentially nests in n-1 step, n-1 asset model, and hence we can first solve a single asset model, and then, which is simple to do, simply by putting the supply of the second asset to 0, and by masking the policies and putting the borrowing constraint also to 0, and then we can solve that model, and then we use the solution of this model to predict the bond price in the zero liquidity limit, meaning we can use this single asset model solution to get the correct expression for the bond price in a model where we introduce a tiny supply of bond. And once we have that price, that's exactly what we do. We start introducing a tiny supply of bond, and then step by step increase the supply of bond, every time retraining the neural network and making sure that every step we have a good starting guess, making sure that the error always remains low until we reach the desired supply. So let's do this in our model economy. Step 1, we set the borrowing constraint to 0, we set the bond supply to 0. Now this is essentially a model with only capital without bond, so the loss function also has only the optimality condition on capital. Then we train the neural networks. Here on the left you see the loss, in the middle you see the asset holding across age groups when we simulate the model. The solid line is on the mean, and the dashed line is the 1 and 900th percentile. And here you see the errors in the optimality condition of capital. So you can see the average error that we have is below 0.1%, so that's very low. Here you see the left-hand side and the right-hand side of the Euler equation. Here I plot the difference. The difference is positive, means that young households on average are constrained, which is very typical what we get in OLG models because of the increasing labor income in the beginning of life. The next step is that we use this limit to get an expression for the bond price in the zero liquidity limit. This will be exactly given by the price that the agent would pay, which most urgently wants to buy this asset. And then we can use that expression to train the neural network to predict the correct price. Note that this is still a function and not a number, because what that price is depends on the state of the economy. And if we do that, we can see the capital policy does not change, because in fact, we haven't changed the model. We just additionally now train the neural network to predict the bond price. And here you can see the difference in the left-hand side and the right-hand side of the Euler equation for the bond. And you can see that it's positive for all households except for one. So what is this? This means exactly that all households would be constrained at this price, except for this one household just before retirement, which is the one that would most urgently want to buy the bond if we introduce it, and hence is the one that is pricing the asset. And now we have a very good starting guess for the policies and prices in the zero liquidity limit, and we can slowly introduce the supply of the bond. So now we add the bond to the economy, we add the bond optimality condition to the loss function, and we slowly increase the supply while always retraining the neural network. So here in red, you see the distribution of capital holdings, and in blue, you will see the distribution of bond holdings. So in the beginning, we only introduce a tiny amount. So you can see there's almost no bond holding. And here on the bottom, you see the optimality conditions for capital and bond for over the age groups. And then we increase the bond supply. And we do this slowly, and we keep training the neural network so that, as you can see, the loss, the mean squared error, never gets too high. So it's about 10 to the minus 6. And that is important because if that error would get high, we would lose our ability to distinguish the two assets, and then the training process could become very unstable. And we keep training the neural network until we reach the desired supply, and in the very end, we will train it a little bit more, just with the final supply, because that's the final model we want. Also notice that because we have the market clearing neural network architecture, we do not need to include the market clearing error here in the loss function, because that is already taken care of by the architecture.
1 minute.
Coming in?
1 minute.
Yes, perfect. So then that's the final error we get. So here you see the consumption on average and the min and max over simulations over age groups. And here you can see the final error for capital optimality and for bond optimality. And you can see the mean errors are well below 0.1% for all age groups. And also the 99th percentile is well below 1%. And then, so to conclude, the starting point is that we now see that deep neural networks are promising to approximate functions, especially with a high dimensional domain, and especially these functions are nonlinear. And we can use this insight to use it to solve models, also as Hanno also just showed us in the previous talk. And the way we do it, the key idea here is that we directly minimize the error in the equilibrium conditions, and that we train the neural network on the simulated path of the economy, which is especially important in high dimensions because we automatically train it exactly where it matters. And then in order to address challenges with portfolio choice, we introduce mark clearing layers, which help us to encode economics into the neural network architecture. And I think this is an avenue which is very promising and which we should try to do more. Also in vision, there are specialized neural networks that do well, and in language, there are specialized neural networks that do well. And I think it's very interesting to think about neural networks that do specifically well for those economics tasks we want to solve. And the second thing is we introduce a stepwise model transformation so that we can essentially start solving a simple model and then end up solving the complicated model of choice by slowly transforming the model in the context of portfolio choice. And in the second paper, we also study a much richer model with housing, equity, and bond, and with this disaster risk, and we study the intergenerational consequences of rare disasters. So if you're interested, I invite you to look at it. And I also again want to point to the other very interesting papers in this quickly growing literature that I'm very excited about. Thank you very, very much for having me. I'm very excited to be here, and I'm looking forward to discussing more. Thank you so much.
Thank you, Marlon. We have about 6 minutes for questions. There's at least one question in the chat by Mauricio, I think. So if you take that one first, and then we can see if there are more in the chat. Otherwise, we'll go by hand raises in the audience.
So there is a question asking, is the pre-trained bond price approach kind of a homotopy analysis method? So yes, so my gut feeling is yes, but homotopy is a strict mathematical word, and I was told that strictly speaking, this is not a homotopy. That's why we're not calling it a homotopy anymore. But the basic idea is that. So we start from a simple model, and then we transform the model in a way that we always remain kind of close to the solution in order to always be able to keep this distinction between the portfolios. And that's why it's also very important to pre-train the bond price, because if you would have a totally wrong bond price, you would just turn on the bond slowly, you would still have large errors, and the whole neural network could unlearn basically the progress we made in a single asset model. So in this procedure, it's always important to really make sure that we have good initial guesses, and that's very much similar to a homotopy method. Yeah, so thank you very much. It's a great question. And then there's also another question. What is my assessment? Will economists skip traditional econometrics and will use deep neural networks as the new standard approach for data analysis? I think it's a great question. I think I'm not qualified, though, to answer this question because I'm not mainly working empirical. I'm mainly working on models and on solving those models. So I'm not qualified to comment. My hunch is that we can never go away from data, because the data is what should discipline us in the long run always. So, but you know, my hunch on this topic is probably not very relevant. But thank you for the question. Thanks.
Okay, are there any questions from the audience? We can still do one or two. Please ask just one question per audience member. Just raise your hand if you want to ask a question. Are there any questions?
So maybe then I can also just add that for the first paper, we have some, if you are interested in your network, you want to get into this, we have some kind of exercise sheets, Jupyter notebooks that have gaps which can be filled in as just for simple models to kind of build up and learn how to use this. So it's also on my co-author's GitHub. So if you're interested, check it out. And I'm also looking forward to check out Hanno's GitHub. I haven't checked it out yet.
Okay, there's a question, but from an audience member who is muted. Can somebody unmute?
Can you guys hear me?
Yes, now we can hear you.
I'm on, and everyone else. Thank you. Thank you for the nice presentation. I'm Danish. I work for the Central Bank of Ireland. I have a quick question around the parameters of these models. My limited understanding of all these models is like we need some parameters. And typically one of the things that I've seen like in developed economies is you can either estimate these parameters from the data that you have, or you can, let's say maybe or you can borrow them from the literature, right? I'm just interested in knowing if there are any developments on the estimation of these parameters in situations where you don't have that much data. What do you do then?
That's a great question. Thank you. So this is maybe more a question related to Hanno's method. So in my presentations, I have nothing to say about parameter estimations. My presentation is my papers are concerned with just given parameters solving the model. And then there's the second layer where neural networks are also very promising, as Hanno has pointed out, that if we have some data, we can use neural networks to directly solve it on parameter spaces to repeat this repeated solving, and then the second step to repeat the repeated evaluation of the likelihood. So maybe I would pass to Hanno for this question.
There's no good replacement, perhaps, for lack of data, but yeah, the Bayesian methods basically are the ones that you might want to look into, where you can, you know, combine your prior knowledge with the data and be more, let's say, data efficient due to that.
Thanks for the question. Thanks.
Okay, if there are no further questions, I think we can go to the final paper of the session by Tohid Atashbar, multi-agent deep reinforcement learning in macroeconomic models. Go ahead, Tohid.
Welcome to this presentation on the multi-agent deep reinforcement learning, or MADRL, and large language models, augmented frameworks for MADRL. So today we'll explore how these techniques can actually create kind of more realistic simulations for the policy analysis. So I know that this is a complex topic, so I'll try to break it down step by step, and I'll try to keep it as a non-technical presentation so we can discuss the challenges and points you may have. So on the motivation, so let's start by discussing the motivation behind this research. So we know that the economy is a kind of a complex system with multiple, interacting agents. So this means that this could mean that the multi-agent modeling could be in some aspects, the most suitable approach for this kind of simulation or analysis. So deep reinforcement learning, which is a type of the AI that learns through a trial and error, allows agents to adapt in ways that mirror real-world economic behavior. So by integrating and then by integrating LLMs, which are kind of the AI systems that, in a sense, that understand and generate human-like text into these MADRL frameworks, we can actually try to enhance how agents make decisions, communicate, and behave. So hopefully leading to simulations that capture the nuances of the real world, complexity. So let's break down the MADRL for short. So it builds upon the key concepts like states, actions, rewards, and policies from single agent reinforcement learning. So in simple terms, this means that the agents observe the environment, take actions, receive feedback, and learn from it. So unlike traditional macro modeling, which often relies on the static equations, MADRL could allow for some kind of dynamic adaptive behavior of economic agents. So this means that we can capture kind of more complex interactions, more nonlinearities, and so that could be difficult with the current models or methods. So MADRL can use different structures or architectures, as we call them, which can be centralized or decentralized with different algorithms like the value-based methods, policy gradient methods, or and more recently, actor-critic approach. So I'll explain in the next slides. So it, of course, also faces unique challenges like dealing with how to deal with the changing environment. So as agents learn, coordinate, and update themselves and the environment. So scaling is another issue. So these challenges have actually driven the development of some specific techniques to improve the learning in the MADRL, and so I'll briefly touch in the next slide. So again, on the basics, just to understand. As I mentioned, that MADRL builds upon the key concepts of the single agent reinforcement learning, so namely states, actions, rewards, and policies. So each agent observes the state of the environment, takes actions based on its policy, and receives some kind of rewards that guide its learning. So MADRL is like, in simple term, multiple players learning a game together. So in this game, each player sees the game board, which is the state, makes a move, which is the action, gets the points, which is the reward, and improves their strategy, which is the policy. So the tricky part is that all players are learning and changing their strategies at the same time, which could make this game changing and more complex, and that if there was just one player or one agent. So on the LLM augmented MADRL framework. So as you know, so the LLMs are the AI systems that can, in a sense, understand and generate human-like text. So this could, in some aspects, enhance the MADRL frameworks for economic simulations. So what this means is that LLMs can process information in the game or in the environment to suggest some relevant actions. which could enable more realistic communication among agents, and which could help model diverse agent behavior. So by integrating LLMs into MADRL, we could create more sophisticated simulations that could capture the nuances of the economic interactions. So in this research, we developed a simple, very basic MADRL framework, which simulates an economy with 6 key agents. So the framework includes an environment simulator, specialized agents, a central controller, and training loops. So I'm not going to detail the technicalities, just basic skeletal one of the simulation. So we used an algorithm called MADDPG, which stands for Multi-Agent Deep Deterministic Policy Gradient. So in simple terms, this algorithm uses for centralized training, but decentralized execution. So meaning that agents learn together, but act independently. So MADDPG uses what we call an actor-critic architecture. So the actor is responsible for deciding the best action in a given state, while the critic evaluates the quality of that action. So this combination of the actor-critic and MADRL setting allows, could allow for more stable and efficient learning. So in this simple framework, we use traditional behavioral macro functions to model the agent behavior and the economic environment. So this is I would say it's just a good starting point, but there are many issues, how to control the behaviors of the agent, how to control for the non-stationarities. So it's still very basic based on the simplified assumptions, but we think that it could be one step for the next advancement. So you can see the framework in action. We tested against the similar models in the traditional macro, but it's not identical, but we think that it's a good starting point. So now, how to integrate LLMs to this framework. So we developed an LLM augmented version inspired by a project called GPT-Team. So this framework incorporates, again, this DDBG, but a multi-agent DDBG, but with the help of help of the LLMs. So we combined this MADRL framework with the LLM capabilities to simulate a 4-sector economy with different types of the households. So in this framework, agents go through a cycle of the observing, planning, reacting, acting, and reflecting. So they use the LLMs to behave and interact. So to me, what's exciting is that instead of relying on the mathematical deductions for agent behavior, like what we do in the macro modeling, we outsource these behavioral functions to the LLMs. So this means that, so it's just a prompt. For example, for the household A, we say that you are a traditional kind of households, you are interested in basic goods. Or for household B, you are a household with, preferences for the green economy. So you like specific sets of the, behaviors. For household C, it's a tech economy or households or something like that. So, so we outsource this decision making to LLM. So this means that we have I call it the double natural simulation. And what is the double natural simulation? The first, agent's actions are guided by human-like reasoning.
Sorry, Tohid, 4 minutes. Yes.
Okay, good. So the first point of the double natural simulation is that the agent's actions are guided by human-like reasoning capabilities by the LLMs. And the second aspect is that is shaped by the feedback received through the interactions with within this simulated economic environment. I mean, through the RL, reinforcement learning, just like we do in our real world. We learn from our mistakes and improve our strategies. And so this is the second aspect of this double natural simulation. So again, we think that this could represent a step towards a more realistic, in a sense, that economics simulation. So this is the framework in action: central bank, firm, government, household ABC, different households with different preferences. They communicate. It's AI to AI communication. They decide by the LLM. And the goal of this exercise is to simulate inflation expectations. So we tell the agents to generate, when they interact and buy and sell goods or something like that, tell the what's the inflation expectation, and then we extract the inflation expectations. So despite the potential, we are still in the first steps. We need to acknowledge that both the MADRL and LLM augmented frameworks have lots of limitations. They still rely on simplified representation of a complex system. There's an issue with the data quality, hallucinations with the LLM augmented framework, and we need lots of computational power. If you need to use the LLMs, you need the API. It's costly. If you need to go with the, accurate LLMs, not just small size LLMs. So there are also risks of bias, misrepresentation, also over-reliance on the simulation results. So addressing these results is crucial, and I think that it requires lots of research. So again, there are some challenges. So aligning the LLM outputs with established economic principles, textbooks, handling uncertainty, improving efficiency, how to handle non-stationarity in the RL. So there are challenges with this, and let me conclude that I believe that the MADRL and especially LLM augmented MADRL could offer some exciting, actually, potential for advancing policy simulation. So there are significant challenges, as I mentioned, but future research could focus on improving, how to integrate LLMs, how to reduce the hallucination, how to control for the bias, conducting more real and comparing with the traditional simulations. And so, and I know that the collaboration across different fields is crucial for some responsible development and real-world adoption of these powerful tools. So let me stop, and thank you. And I can look at the chat.
Thank you, Tohid. I think we have at least 3 questions in the chat, starting from Natasha's comment. So if you want to respond, we have about 8 minutes for the questions.
The first question is how to choose the network structure, type and size for actor. So it's a bit technical question. I'm not sure it's good to discuss in here, but we can discuss later. But just as a starting point, actually, there's no good answer for this. We could start by very simple structure, very, small size type, and then, run the model to see what's happening. So these models are kind of the black box models. You can't actually explain what's the a difference between the exact, the actor and critic with this size and that type. You need to just, fine-tune the model by running and comparing. So the bottom line is that there's no good answer for that in the literature. It's just research and development trial and error. So another question, again, you're doing for this. You're doing automated prompt engineering for the single. I'm not sure. Can you unmute and explain your question, automated prompt engineering? Mauricio? I can explain some, but if you can explain your question.
Who should be unmuted? Can you repeat? Mikael?
Mauricio should be unmuted. Has anybody unmuted Mauricio?
Maurizio?
I think we are having a problem. Maybe you take Alvaro's question first, and then we can return to it.
Okay, so you're working on the engine, find the problem. Yes, so on the replicability. So again, this is so you need, we need to start with the very manageable, sets of the agents and environments. And if it's an LLM augmented framework with a very simple prompt, and then run multiple times to see whether there are similarities with the different runs. And then when you see the, the similar trend across different runs for different variables, you can add, this is my style of expanding the model. I add, another agent, go from a simple prompt to a more extended prompt. But if you start with a very complex, MADRL, also very detailed prompt in the case of the LLM augmented ones. So yeah, you can't replicate without just by running again. So there is no, there's a limited literature on that. So you need to find your style for now as we produce, the literature and yeah. So okay.
Okay, perhaps we can have Mauricio.
Oh, yes. Now, Tohid, can you hear me?
Yes.
So thank you very much also for your presentation. What I wanted to ask with my question is, how do you update also the system messages or the prompts also for the LLMs which are embedded within your approach? This sounds to me like prompt engineering and automation with the interaction with the environment. Is that the case?
Okay, good question. So you start from with the first or initial prompt or the system prompt, as they call it in the the ChatGPT or other frameworks. But then you'll take from there, and you need a memory that the agents need to receive and communicate each other. But so, for example, the agent A, household A, says that I'm going to the market, buy something. And household B says in response, and this message is propagated to all agents, and all AIs listens and hears this specific request. And then they update the environment through the RL. And then based on the system prompt, they think, it's called the thinking. And then they go to the reacting in the, the terminology of the LangChain, if you are familiar with it.
Yeah.
And then you have a memory, and then they pass it to the LLM, they receive the response. But the basic system prompt is the same.
So that means that a conversation is just also getting bigger and bigger during the system run, and you have a conversation that's they draw their knowledge of.
Yes, exactly. And you need to have another mechanism for the, so there are lots of conversation, lots of inputs, but you need to save or memorize the specific or more, important ones. So you need another prompt or another mechanism to how to select or how to, the save, or memorize, and how to remember the communication. So there's another part of this framework.
In that case, maybe I think that it's maybe interesting for you. I'm going to post it on the chat. There is a new project by, I think it's the Stanford University DSPy, which is kind of a thing for programming LLMs and optimizing the prompts themselves. I don't know if this is also interesting for you or anybody else. That might prove to be a good thing to also implement. I mean, I now understood your approach, that you're letting the conversation to grow, but in order to really automate the prompt engineering, that seems kind of maybe related.
Yeah, I looked at the link and it looks very interesting. So I'll make sure to look at it and use actually. Thank you.
Thank you very much for your presentation.
Of course. Thank you.
Thank you very much, Tohid, and big thanks to all three presenters. I think this was a very good session, and I think we can, on behalf of the entire audience, I can extend thank you for these presentations. With no further ado, I think I pass the word to Alessandro, who will moderate the next session. Alessandro, go ahead.
Thanks. Thanks, Mikael, and welcome to the second session, which will be about machine learning and artificial intelligence applications to business cycle and inflation forecasting. We're going to have two contributions from the academia. The first one is about a very topical issue, I would say, these days, especially in central banks. That's about core inflation. And the first speaker is Philippe Goulet from Université Québec and Montréal. And the second speaker is going to be Kim Ristolainen from University of Turku, who's going to speak about the exchange rate. So we will have 15 minutes for presentation, and that will give us 5 minutes for Q&A at the end of each presentation. So I'll give the floor to Philippe.
Hello, everybody. Thanks for having me. I guess I'll go right into it, given that we have 15 minutes. This paper is called Maximally Forward-Looking Core Inflation. So the objective is really, at least what it is, to build a maximally leading measure of core inflation. I'm Phil from UQAM. Also, we have a lot of other people on this paper. We have Karin Trieber from the Österreichische National Bank, and Christophe Barrette, who was my student at UQAM and now starting his PhD at Bocconi, and Max, who is also at Bocconi right now. So the motivation is pretty simple. I mean, these are a year-over-year measure of inflation in the US. You have the pale blue is headline inflation. And then you have core inflation in the darker blue, which was usually defined as taking out food and energy. And then you have the trim mean inflation, that used to be quite popular, still is. And you have them here, and what I want to draw your attention to is what's going on after the dashed line here, but also a bit during the Great Recession. You see that the core measure, but especially the trim mean one, seems to be lagging. If you look at the variations that we might want to be able to capture in real time, as things are unfolding, I mean, we see that the green line is sort of going up and down, maybe like 4 or 5 months before the other measures. And the question is there a way, in fact, to address this and build a core inflation measure that might have better leading properties? And I think it's good to know that this is not just an artifact of using year-over-year measures, which are ubiquitous in macroeconomic monitoring. I mean, even if we put this in quarter-over-quarter, so 3 months average instead of 12, then we see that, in fact, it's still going up and down a bit slowly. So just a bit of a landscape view for core inflation measures if you're not really familiar with them. So some of them are based on heuristics. Permanent exclusion is what it is. So the typical core, the one we usually call core inflation is, we, like I said, we take out food and energy, but you can take out more stuff if you want. And those are based on some kind of heuristics, and definitely they're widely used in many countries. And then you have other heuristics-based measures based more on temporary exclusion. So you have something like median inflation and trim mean inflation, where some kind of trimming rule based on the distribution of price growth rates is used. And just to be clear what is done for trim mean inflation, you look at all the prices, you look at all the growth rates of all these components, and you say, okay, the most extreme at the bottom of the distribution in this month and the most extreme at the top of the distribution in this month are going to be taken out, and we're going to take some weighted mean of whatever is left. And in that way, you already been taking out a lot of volatile things because you mechanically just trim the tails. And then number 3, we have model-based, so factor models oftentimes of core inflation. So you have the multivariate core trend maintained by the New York Fed, and in the Euro area, we have the PCCI. So what are the desirable properties, right? We have many measures, and what is commonly accepted as the desirable properties is to have low bias, low volatility, and low error in forecasting headline inflation. So low bias makes sense. It has to be a measure of inflation somehow. So its mean should be far from the mean of the real headline inflation. Low volatility, so we can have a look at it, and signal should be stronger than noise. The number 3 is quite interesting, right? It's about where is inflation going next, right? We know where inflation is right now, but for the purpose of monetary policy, we probably want to have some kind of indicator of where it might go in the near future. And having low error in forecasting headline inflation for a core measure appears to be quite desirable to meet this objective. And last point is highly reactive to monetary policy and labor market conditions. So that's the idea here of the Phillips curve. So that's the 4 things you'd like to have. So in this paper, we write a somewhat simple machine learning regression problem that will generate by construction the weighted average or the linear aggregation of subcomponents that will be maximally predictive of future inflation conditions. We're going to call this thing the assemblage regression, and the resulting core measure we're going to call it albacore, because that's an adaptive measure. First of all, it's going to adapt to whether you're forecasting short run or long run headline inflation, and it's based on machine learning, so learning-based core inflation albacore. It's going to feature our first 3 objectives by construction, and then the 4th one is we're tackling that in a subsequent project. So that's the only math in this talk, but this is fairly simple math because this is just like a regression with a few constraints. Here we have the target, which is headline inflation between next month and the next H months, which could be the next 6 months, 12 months, 24 months. We have the subcomponents matrix here. So all this matrix just has, all the disaggregated inflation series. We can have highly disaggregated series, can even have like micro data in there. And then we have a vector W. These are weights, so we're going to be allocating weights to the different components. And this part here of the minimization problem is just least squares. So we're just going to try to find a linear combination, a weighted average of these components, so that it's as close as possible, not to inflation right now, but to inflation in the future. So another way to see this, the loss function that we have, is trying to find somehow a consumer, here described by its vector of consumption weight W, a consumer right now in time t that is maximally indicative of the average consumer as defined by the statistical agency in the next, say, 12 months. So what's going on here is just adding constraints and things that will make this work. So first of all, the weight should be non-negative. That's fairly intuitive. The weight should sum to 1, so it should be like a real consumption basket. That's the budget constraint in a way. And here maybe is the only more sophisticated thing. This is a ridge, some kind of generalized ridge penalty. We're going to shrink the weights in estimation to the official weights. So to tell the algorithm that yes, we want to have an allocation, but that allocation, especially if we're running this regression on 250 components, so it has a lot of potential for overfitting. In that context here, we're going to shrink the weights to the original ones, so to avoid that. And it sort of makes sense. This L2 norm here just says, well, we're going to have an allocation. It cannot be miles apart from the original one, and it cannot be overly sparse because nobody would think with highly disaggregated data that we could get a core inflation measures that's only based on eggs, beer, and chairs. For instance, we were expecting, in fact, to have a pretty wide basket. So that's the first one. We call it albacore comps because it operates in component space. In the second equation here, we have albacore ranks, which is going to operate in rank space. And this is sort of a version of a trimming indicator. This operates by including and excluding components and weighting them. Here it's going to include and exclude parts of the price distribution. So it's not going to be always some of them are in, some of them are out. But in fact, what we're going to have here is weighting order statistics, weighting different part of the price distribution at each point in time, so that we're looking at the whole price growth distribution and putting the highest weight on the part of the distribution right now that is most indicative of what's going to happen with the average in a couple of periods. And this is fairly simple to do. It's just ordering the data, putting it in a matrix. So at each point in time, you just sort all the components, you stack them in a matrix, and we run this regression. Then the regularization must change to accommodate that this is not just components anymore, but this is going to give us supervised trimming with albacore ranks. We do a couple of experiments, not going to get into so much detail, but just to give you a bit of a sense what this machinery can do, we are going to do it for different levels of disaggregation, from reasonably highly aggregated to highly disaggregated. So that will go from 15 components to 215 in the US. In the Euro area, it's 12 to 92. We're going to compare it to a suite of benchmarks, and we can also check with out of sample performance in 2 different inflation regimes, so pre-COVID and post-COVID. And in pretty much all of these setups, albacore comps and albacore ranks show good performance in terms of mean squared error at pretty much any level of disaggregation. So the question is, what does this thing look like? These are the results for the US data. So again, we have the traditional inflation measures in here, and we have albacore ranks and albacore comps. And what I think you should notice right away, for instance, albacore ranks first doesn't tank nearly as much during the Great Recession, but also, I mean, you see here we still have this green line from trimming quite lagging. Our supervised trimming version is going up, but almost, I don't know, 5 months before the other one. In fact, it starts to climb up in mid-2020. So it seems to be achieving its objective of being maximally forward-looking. And what we see here, this panel, is the trimming that we get from a regression. The greenish part of this plot is the sort of the trimming that you would usually do. So you take out the bottom, you take out the top, and you focus on the mid-range. But we see the black part here is in fact the weights on the ranks that albacore ranks has, and it's the result that we get is that the optimally forward-looking trimming is in fact a highly asymmetric one. The distribution puts a high focus on around the 70th percentile, whereas typical trim measure would put a lot of weight on the median. When it comes to albacore comps, we see that some of the traditional wisdom remains. Energy is pretty much taken out. If you compare the red, which is this usual allocation, to what we get in dark blue, then you see it's pretty much taken out. And then food goods is not completely excluded, but it's has a diminished weight with respect to a headline. So that's again a bit more aligned with the wisdom. So the big key difference, I would say, happens in the trimming space, where we have a highly asymmetric trimming results. So I'm not gonna
If you have about 3 minutes.
Yeah, good.
Thanks.
So if you look at the historical decompositions, which is something you can do in component space, in rank space, you can compare it to standard measures. We see again albacore ranks very different from trim min. Trim min, by focusing on the median, puts a pretty strong weight on shelter, which is known to be lagging, definitely at least in the US. And we see instead albacore ranks put a very small weight on shelter, but instead puts an increasing weight on good inflation, which was in fact driving the whole thing, at least in 2021 in the US. So it's pretty strong, whereas in the other trim measure, it's not there. And it sort of makes sense because the early goods price increases were definitely in the upper tail. So if you're excluding that a priori, then you cannot capture it. So the methodology is pretty flexible. I mean, this plot might look a little crazy, but you can look at the weights depending on the horizon. If you want to focus on 12 months ahead inflation, or 1 month ahead, or 6 months ahead, then you can study what your allocation of a maximally forward-looking core inflation should be. So this is just to a bit tell you how adaptable the methodology is. You can also do the same thing for ranks, and what we see is that the asymmetry in the rank really sort of starts to settle once you're looking more than 4 months ahead, approximately. And then maybe another thing worthwhile to know is that this is a very easy to adapt environment. For instance, if somebody would like to build a core inflation measure that was specialized for inflation tail risk, so very high inflation, or for deflation risk, then we can change the main regression to a quantile regression, and then the way is the assemblage way. So you're going to adapt and specialize for these different risks. So this is something you can do. This is something we do in the paper. So I'm going to wrap up with, some brief thoughts. So in these 15 minutes, we devised 2 simple maximally forward-looking core inflation measure from disaggregated data. It's part of a broader research agenda where we macro aggregates are partly redefined by a machine learning algorithm so that they better satisfy some statistical evaluation criteria. It can also be an economic one. You can think about core wage growth or core GDP. You can use more micro level data. And then circling back to the theme of this workshop, which is the application of AI and machine learning in macroeconomics, I think, what the key idea here is supervised aggregation. So this is one of the key building blocks of modern deep learning. And the way I want to connect this with modern deep learning is to say that what we do, rather than building manually predictors from these aggregates, one can, in fact, endogenously construct the features from unstructured inputs in a supervised way in an image recognition system that would be pixels we would use rather than microprice data. And we do so through some layers, but here, what we're really doing is optimizing everything jointly with the forecasting model that's going to end up using it. So I think I'm out of time. I'll stop here, and I'll thank you for your attention.
Thanks, Philippe. That's a very interesting presentation with a lot of results. I see no question as of yet in the chat, so I encourage people to type their questions. There's one now, which I guess you can read, otherwise I can do it for you.
I think I've seen it. Let's see. maybe I'll read it for everybody to hear. So maybe I missed, how did you find the optimal lambda? How did you find the range of possible lambda values? Yeah, as you understand, and I went a bit quickly over some of those details, but yeah, for lambda, we do what people do. We use cross validation to get the lambda, and maybe the only detail I might be worthwhile to mention here, since this is time series data and highly persistent data, because we're forecasting ultimately moving averages of inflation, it's better to do some kind of block approach for the sampling procedure and the cross validation. Otherwise, you might end up choosing a bit too low of a lambda and go back to overfitting. So we do standard cross validation with blocks, and the range of possible lambda value, I would just set it manually to be as large as possible so that we don't hit on the bounds, which is, I guess, what anyone should do. So that's it.
While we wait for another couple of minutes, we have time for a few more questions. Otherwise, in the meanwhile, I will take advantage of my role and just ask one question myself. All right, there's one question in the chat, so please go ahead. Question is, could you please share your slides and maybe a draft of the paper? Yeah, I had a question. Actually, you showed interesting results for U.S. inflation. Do you have some sort of similar results in comparison to existing measures for the euro area as well? That was my question. And there's another one in the chat, if you want.
Yeah, I'll pick it up right after. So regarding euro area results, in fact, yes, we do. I decided to, my co-author was presenting it at another SUERF event 2 or 3 weeks ago, and she was presenting the euro results. So I thought I should focus on what I know better, which is the American results. But yeah, in the paper, we actually study the two cases in parallel. We also study it for Canada, which is also interesting because the data here is not always as good as you'd like it to be. But yeah, for the euro area, we actually have similar result that we see supervised trimming helps. It's not as clear as in the US. I mean, the asymmetry in the trimming that we get in the euro area is not nearly as pronounced as we get in the US. So I remember that. And then in the component space, we also get that it's not immensely different from the usual core, but still you have a bit of these reallocation. And when you check forecasting performance, in fact, for COVID, the COMS version for the euro area does quite better. And we have also similar things for Canada. Now, all of this is in the paper. I think the first question in the chat, it was, can you share your slides and the draft of the paper? The paper is on SSRN and archive. And the slides, I think they might be on my website. I can put them, or maybe I can send them to SUERF. Maybe it's going to be shared. Anyway, well, happy to share everything we got. There's also a package, by the way, if you ever want to try this. The assemblage regression, you can put your own stuff in the package. You don't need to code these constraints or this ridge thing or this cross-validation even. It's all packaged in the assemblage regression package in R. So that's, I guess, pretty convenient too. Now, do I understand correct?
Yeah, you have just like 30 seconds for the final question before we move to the next paper. Yeah, it's about the signal. Yeah. Do you understand correctly that you get the signal from inflation before it actually materializes? That's the question.
If I have to understand quickly, I'll say yes. I mean, this is not a silver bullet, obviously, but it's a core inflation measure that is better able to signal inflation before actually materialize. So voila.
All right, thank you. Thanks a lot, Philippe. And we can move now to the second and final paper of the second session. The author is Kim Ristolainen from Université Turku. Kim, the floor is yours.
Thank you for the opportunity to present this paper here. So the title of the talk is Exchange Rate Narratives, and this is joint work with Vito Kormun from Santa Clara University. So in this paper, we offer a procedure to explain macroeconomic indicators with information from the news media. And we specifically target the dollar exchange rate in this paper. So why do we focus on the exchange rate? So many of you are probably familiar with the fact that analysis from standard time series for exchange rates are inconclusive. So Fama, for example, found this low R squared, and Bacchus and Smith found these wrong correlations, implying that the economic theory implied predictors of the exchange rate actually have insignificant coefficients in empirical models, and in many cases the coefficients even have wrong signs. Mies and Rogoff also showed that these economic theory-driven forecasts are actually quite poor for the exchange rate. So there's this sort of disconnect between the economic theory that says that these things should explain and predict the exchange rate, but we observe something different in the empirical literature. So more recently, there has been some progress on this issue, and a couple of papers have shown that actually fundamentals explain the exchange rate somewhat, at least in specific subperiods. So in this paper, we thought that news information might help in giving new insights on this sort of exchange rate puzzle where people are wondering why the exchange rate is so hard to predict. We think that news might help because market participants, when they form expectations about the exchange rate, they probably are looking more at the actual news than observing specific macroeconomic statistics. So a very quick overview of the findings of the paper. So first, we show that news contain useful information about the exchange rate. So news text derived predictors outperform predictions of standard macro indicators. Secondly, the topic model that we use to extract the predictors from these news texts sort of favor this epidemic-like decomposition of the exchange rate. So this means that specific topics in the news explain the exchange rate in a specific period. And we also show that the relationship between the exchange rate and the fundamentals might be or is likely to be a nonlinear one. And finally, these results sort of are informative for exchange rate theories, more so to the scapegoat theory, which states that market participants might sort of select this one specific variable as a scapegoat. So they think that one specific variable at the moment is driving the exchange rate. And when this variable becomes the scapegoat, then that there's a feedback, and that scapegoat actually becomes a driver of the exchange rate. Then when time goes by, this scapegoat might switch to a different variable. So, yeah.
Oh.
Yeah, so I'm going to skip the literature quickly because we have so few minutes left. So I'm going to straight into the procedure that we use to extract information from the news. So we use this SLDA model, which is the supervised latency relay allocation model. And this is an extension of the most commonly used topic model called the LDA model. So what this LDA is, it's an unsupervised machine learning method that is often used to extract these latent topics from a corpus of text data, which in our case are Wall Street Journal news titles. So I'm not going to formally present the model, but I'm going to sort of generally tell what's important to know about the LDA. So what the LDA sort of provides us when you have estimated the model. So it provides us with two different important things. First, it will give us the topic distributions for each of the news title that we have in our dataset. So this will basically tell us that the specific news title is for example, 20% about topic 1, about monetary policy, for example, and 80% about fiscal policy topic. Then the second component that we get from the LDA are these word distributions for each topic, which reveal that which words are more common for which topic. And this information can be used to sort of look what these topics are about and also give names or labels to these topics. So the supervised LDA in our paper that we use is an extension of this basic model, so that when forming the topics in the model, it is assumed that there's a response variable that could be predicted with these topics that have been formed, or it's possible that they have a predictive relationship. So this SLDA sort of maximizes the predictive power of the topics that are formed from the text data. So we have over 700,000 individual Wall Street Journal article titles in the data set from 1975 to 2022. And the response variable in the SLDA that we use is the monthly real exchange rate of the US versus the G6 countries. And because this response variable is a monthly variable, we also have to provide the SLDA text data in a monthly format. So we had to pool all the news titles that have been published in the same month into this large meta title, basically. Then after optimizing the hyperparameters of the model, we ended up estimating the SLDA with 180 topics as the final model. And this is a very common number of topics found in different papers using topic models and this Wall Street Journal news data. So after this SLDA extracts these topics from these text data, we can use the topic distributions for each month to form this sort of time series of the frequencies of these 180 different topics in the news. And when we have done this, we perform the following things. So we want to select a subset of these 180 topics that have the highest predictive power over the exchange rate. Then we use the topic distributions that tell us what the topics are about to cluster these individual best performing topics in a few meta topics. And we do this because we want to sort of have more general topics to figure out what is sort of driving the exchange rate. And finally, we examine the relationship between these meta topics and the macroeconomic indicators. So first or secondly, the prediction exercise with these topics. So we estimate a random forest machine learning prediction model to predict the monthly level of the real exchange rate and its changes with different horizons and with different sort of predictor sets. So first we use all of the topics to estimate the model, and then we use all of the 120 macroeconomic indicators that can be found in this FRED database. Then we combine these two information sets and estimate a new model. And finally, we select the best performing topics, so a subset of these topics to estimate the random forest. So basically in this table, we can see the out-of-bag R-squared values for the predictions. So out-of-bag here refers to the observations that were not used to estimate the random forest model. So basically these observations can be used to evaluate the prediction ability of the model much better than the in-sample results. It's not out of sample, but it's sort of a good approximation of the out of sample performance. And from this table, we can see with using only the topics, we get much higher out-of-bag R-squared values than when using the macroeconomic indicators. And what's even more sort of better result is that with only 16 topics, we get close to the same R-squared values as with all of the topics. And sort of after this result, we can, or from this table, we can first conclude that, okay, topics are highly informative for exchange rates, and they are actually preferred over these macroeconomic indicators. And we sort of tested this by calculating the feature importance of each predictor in the model that uses both macroeconomic indicators and these topics. And among the top indicators across different horizons, most of them are topics. Some are still macroeconomic indicators related to the housing permits and bond spreads, but most are topics. So after this, we wanted to form the more general topics from these very useful individual topics. So we used a clustering procedure for the word distributions of these individual topics. And the purpose here was to sort of group the individual topics that use similar vocabulary into these more general, fewer topics. So we have 6 meta topics constructed from these 16 individual topics that you can see here. So we use ChatGPT to label these individual topics. We provided the word distributions for ChatGPT, and then we asked it to give some kind of label to the individual topics given this information. So then we tried to figure out that, okay, what if we use only these 6 meta topics to predict the exchange rate? And you can see the R-squared values for that exercise in the last column. So also in this case, the R-squared values sort of reduce only slightly. So we get almost similar explainability of the exchange rate with only these 6 meta topics, which is quite interesting. And then when
you have about 3 minutes. Thanks.
Yeah, thanks. So when you plot the frequencies of these meta topics, you can see this sort of disease kind of like behavior that when one meta topic increases and peaks and declines, the other ones are sort of down, and then another one takes their place. Then we looked at the actual predictions of from the random forest model. So we plotted the contributions of each of these 6 meta topics on the prediction of the monthly real exchange rate, and these different colors here represent different meta topics. And from this picture, we can sort of see that during the first part of the sample, these meta topics 1 and 2 explain the exchange rate the most. Then around the dot-com bubble, meta topics 4 and 5 do the same thing. So this sort of points toward the conclusion that the exchange rate is explained with different things in different time periods. So although we labeled these topics, we still wanted to figure out a little bit more what they are about. So we did the exercise of estimating the random forest again, but now we predicted the fundamental variables with these 6 meta topics. Then we calculated the feature importances of the predictors for each decade and for each model. So from this picture, we can sort of see which predictors are the most important predictors of a specific variable in a specific time period. And from here, we can conclude that the meta topics 1 and 2 are more related to the federal funds rate and the government debt, whereas the meta topics 4 and 5 are more related to the S&P 500 and the VIX index, so more related to the financial markets. So, and also we did the same for the total factor productivity, and found out that the meta topic 6 that was labeled as technological advancements and financial reporting is the most important predictor of this TFP. So in sum, the exchange rate changes can be explained by these meta topics or narratives, and these narratives are differently related to fundamentals. So if this is the case, we should then observe something in just estimating standard macro regressions explaining the exchange rate, so without these narratives. So as a final slide, I'm going to show you some simple rolling window linear regressions where we try to predict the annual change of the exchange rate with these macro variables. And from here, we can see that the R-squared for the rolling window regressions is always much higher than for the model that uses the full sample. And also the coefficients of the fundamentals are sort of highly unstable, meaning that they are highly significant in some periods and in some periods they are not. And when they are significant, the coefficients are consistent with with our metatopic analysis mostly. So to conclude, we use this novel procedure, the SLDA, to extract news media info on a time series of interest. Then we showed that the anatomy of the exchange rate sheds light on long-standing puzzles, and it seems that the sources of the exchange rate fluctuations vary over time, and this is consistent with the scapegoat theory. So that's it. Thank you.
Thank you, Kim. Thanks a lot for a very interesting presentation. I see there's one question in the chat if you want to read it and
yeah,
reply. And then I have a short question if time allows. Thanks.
Why do you choose the real exchange rate as response variables, not nominal one? So I have to be honest that I'm not the real exchange or the exchange rate guy here. I'm the machine learning guy, and my co-author is the exchange rate expert. So I have to ask from him why it was important to select the real exchange rate. And also the second one, I'm not sure about this. What inflation measure do you use to compute the real exchange rate?
There's another question by Ernest.
Yeah.
So let me read it out in the meanwhile. The question is that the Euro system in its Malware projections uses a random walk for the exchange rate assumption. And the question is, with your findings, do you think this is obsolete, or should your method be used in the future instead?
I'm not sure, because we are still ourselves, we are a little bit skeptical about the results. So there might be the issue of like spurious regression going on here. And we want to sort of add and confirm these results with like a monthly change in the exchange rate, which is not that persistent of a variable, because these are using the level of the exchange rate and these longer horizon changes, which are stationary, but they are very persistent. So it might be the case that the trends of the metatopics and the trends of these variables are the reason for these high R-squared values. But what we are doing next is that we are running this whole procedure from the beginning with the monthly change as well. And we try to add some like real out of sample results as well to confirm this, because the R-squared values seem quite high, but still many models in the literature, they use a linear framework. So they don't use like machine learning models. So it seems to be the case that the relationship is also a nonlinear one. So I don't want to make any sort of answers to your question, because I'm not quite sure about the results yet, but these at least point toward the fact that the exchange rate is somewhat explainable with this metatopic.
All right, thanks a lot. That concludes session 2, and I will give the floor to Ernest for concluding remarks. Thanks a lot.
Thank you, Alessandro. This concludes our SUERF-ECB Bank of Finland, Bank of Italy workshop on the use of AI in economic modeling and forecasting. Thanks to our speakers for your very informative and stimulating presentations, to Mikael and Alessandro for moderating, to the scientific committee for putting this together, and to all of you for your interest, participation, and your many questions. Bye-bye and take care.
Bye-bye.
Bye.